Where is the universe's center located? It's time to clarify that the universe doesn't have a center, contrary to conventional cosmological beliefs about its structure. A center point would need to be unique in some way compared to the rest of the universe for it to exist, and one should also attempt to define the center of the universe. For example, it could be described as a center of rotation, or is it a mass center? Maybe something like the center of mass, or a center of charge, an item where the average quantity of electric charge is the same in all directions around it. The point of curvature center might be it, or a point of growth. Last but not least, the center of the universe might be a singularity, such as a supermassive black hole or a superlarge nebula. But observations show that different kinds of objects are dispersed randomly throughout the cosmos, and the laws of physics themselves show that there is no center of rotation, mass, charge, expansion, or curvature. Nevertheless, what's interesting about this is that at one point, humans thought we were the center of the universe. To try to comprehend why there isn't a center to the universe, it could be worthwhile to in some way retrace the historical and cultural steps that got us here. Let's start now. Based on astronomical observations, Greek philosophers created the geocentric model in the 4th century BCE, which postulated that the sun, moon, planets, and stars revolve around a stationary spherical Earth at the center of the universe. Ptolemy of Alexandria's geocentric model was the most advanced. In 2nd century CE, he studied Greek cosmology and held that the Earth was at the center of the cosmos, surrounded by numerous spheres. Because geo in Greek means Earth, the hypothesis is known as the geocentric theory. Through his own eyes, Ptolemy perceived the cosmos as a collection of spheres revolving around the Earth, which was at their center. Ptolemy believed that the Moon, Mercury, Venus, and the Sun all rotated around Earth because that was the only way he could understand the cosmos. Ptolemy used Hipparchus's idea of epicycles, put forward a few centuries earlier, to figure out his calculations because he was unsure of his explanation of the universe. Epicycles were thought to be tiny, unseen circular orbits that were moving on planets. Astronomers were supposed to have validated Ptolemy's hypothesis with this and his tables, and for many years, people accepted Ptolemy's theory. There was evidence for the geocentric paradigm that seemed rational. First of all, wouldn't we feel the Earth moving or sense a strong wind blowing in the direction of the movement? Also, wouldn't we observe the stars move if the Earth actually did revolve around the Sun? Because to the great distance between stars, this final phenomenon, known as parallax, is genuine but much too small to be observed without a telescope. Until recently, it was believed that the Earth was the center of the universe, and it actually was. Up until the 16th century, when a brilliant man by the name of Nicolaus Copernicus created the so-called heliocentric model, this notion was largely believed. Indeed, a number of others had the same thought in their heads before him. The doctrine of the Christian Church, however, was already largely established at that point and had been greatly impacted by the geocentric model and Greek and Roman philosophers. Because it is in human nature to want to feel special, the geocentric paradigm places humans in a special position at the center of everything, which is why this way of thinking was generally diffuse. Your religion therefore offers as one of its core tenets that you are not only a unique individual, created especially for you by your divine existence, but that you also reside in a unique location at the center of everything. Even though Copernicus never agreed with the Earth-based theory of the universe, he did not express his opinions in public until he was quite old. In reality, everyone who disagreed with church teaching has been labeled as a heretic, which may lead to your reputation being ruined, your being imprisoned, your being put to death, or all of the above. The notion of a heliocentric, or sun-centered, system predates Copernicus. In actuality, Aristarchus of Samos had put out the idea that the Earth rotates around the Sun in the 3rd century BCE, but the majority of other ancient astronomers had rejected it. The first modern person to promote this idea was Copernicus. It was able to readily explain phenomena that the geocentric theory found challenging, most notably the planet's apparent retrograde motion. In the sky, the planets typically move eastward, but occasionally they unexpectedly reverse directions and move westward. The geocentric model made an attempt to address this by increasing the number of orbits the planets will take. The heliocentric hypothesis, however, explains this by simply reversing the Earth's motion with respect to the planet being viewed. To avoid persecution by the Church, Copernicus delayed the release of his book on the revolution of the celestial spheres until after his passing. What came next is frequently referred to as the Copernican Revolution, yet this wasn't really much of a revolution. The book could not be read by the general population because it was published in Latin. Academics could, but few knowledgeable individuals were prepared to risk their lives in front of the Church. Even then, in 1616, 73 years after its initial publication, the Church did not deem it significant enough to list it on its index of forbidden books. The Copernican revolution was the paradigm change from the Ptolemaic model to the heliocentric model. Certain individuals stood out from the crowd, which helped to advance the Copernican revolution. They were Johannes Kepler and Tycho Brahe. The main accomplishment of Tycho was his significant advancements in the field of observations. Newer, more precise observations than those Copernicus used would be necessary to expand our understanding of the cosmos. Tycho Brahe noticed a brand new star in the Cassiopeia constellation in 1572. It was evident that it was a star in the heavenly realm according to the Grecian and Christian models, since it shined brightly in the sky for 18 months without any discernible parallax. Tycho's observation was a huge blow to the hypotheses because, in that model, no change could ever occur in the heavens. Tycho noticed a large comet in the sky in 1577. He determined that the comet went through the area of the planets based on his parallax readings. In accordance with the previous assumption, this zone was only capable of uniform circular motion on solid spheres, making it impossible for a comet to pass through. Tycho came to the conclusion that such spheres did not exist, raising the issue of what maintained a planet's orbit. As Tycho Brahe's assistant, Kepler was employed. He was thus in a position to use Brahe's thorough observations to produce outstanding advancements in astronomy, including the 3 laws of planetary motion. The following is a summary of Kepler's 3 laws of planetary motion. 1. The path of the planets around the Sun is elliptical in shape, with the Sun's center being situated at one focus, the law of ellipses. 2. Equal areas will be covered in equal amounts of time by an imaginary line stretched from the Sun's center to the planet's center, the law of equal areas. 3. The ratio of any 2 planets' squared periods to their squared average distances from the Sun is equal to 1, the harmony principle. They made such a significant contribution to a fresh understanding of how the universe fits in with our world. Galileo Galilei arrived after Kepler. He created a telescope with a powerful enough magnification to enable him to observe Venus and learn that it had lunar-like phases. The 4 main satellites of Jupiter, Io, Europa, Ganymede, and Callisto, were also found by him as a result of his observation that some objects were orbiting Jupiter. It was July 1, 1610. The discovery demonstrated that not all solar system objects orbit the planet Earth, which was a major argument in favor of Copernicus' heliocentric hypothesis. The geocentric idea was now extremely challenging to support. But on July 5, 1687, the Philosophiae Naturalis Principia Mathematica, Latin for Mathematical Principles of Natural Philosophy, was published, dealing the old model a fatal blow. It was written by Sir Isaac Newton. The Principia lays out Newton's laws of motion, which are the cornerstone of classical mechanics, as well as his law of universal gravitation and how Kepler's laws of planetary motion were derived from it. Kepler's rules were derived empirically. The greatest contribution of Newton was to provide them with an analytical framework, a description, and a physical justification. Newton created and applied mathematical techniques that are now employed in the study of calculus in order to construct his physical ideas. He is the reigning calculus king. The sun was at this time the center of the cosmos and was therefore the center of the universe. What took place next? The early 20th century saw the creation of cosmological models of a homogeneous, isotropic universe that lacks a center and is expanding at all locations as a result of the finding of additional galaxies and the development of the Big Bang theory. There was a common belief before to the 1920s that there was only our own galaxy, see for example the Great Debate. So, there was no difference between a hypothetical galaxy center and a hypothetical universe center in the minds of astronomers of earlier eras. Thomas Wright was the first to accurately postulate in 1750 that the Milky Way might be a body made up of a massive number of stars bound together by gravitational forces and spinning around a galactic center. Immanuel Kant expanded on Wright's theory of the Milky Way structure in a paper written in 1755. Galactocentrism, a type of heliocentrism with the Sun at the center of the Milky Way, came to scientific consensus in 1785 when William Herschel offered a model based on observation and measurement. The Milky Way was now at its center, and the Sun was no longer the center of the universe. It was also the sole galaxy. However, the startling discovery of novae within what was then known as the Andromeda Nebula raised the possibility that the Milky Way may not be the only galaxy in the universe because those novae were significantly fainter than novae in the Milky Way, and Andromeda was thought to be located at a distance of 500.000 light-years. It was impossible for an item so far distant to belong to our galaxy. Nonetheless, this was remained up for question until 1925, when Edwin Hubble discovered extragalactic Cepheid variable stars on telescopic images of M31, putting an end to the argument concerning the existence of other galaxies. Moreover, Hubble showed that other galaxies' redshifts are related to their separation from the Earth. It is now known that the metric expansion of space is what causes the redshift observations of Hubble, in which galaxies appear to be moving away from us at a rate proportional to their distance from us. This is an intrinsic expansion in which the size of space itself varies, increasing the separation between two distant regions of the universe over time. All of this culminated in the so-called cosmological principle, which asserts that the universe is isotropic and homogeneous. Observers can access the same empirical evidence throughout the universe, and the same observational evidence is available by looking in any direction in the universe. Ladies and gentlemen, an isotropic, homogeneous universe does not have a center. Leave a comment below and tell us what you think.